All right. So is this our? This isn't us, is it? No. Is this us? No. This is us. All right. So last time we started. What, is this us? Did I?
Yes. Yes.
Oh, did I not actually start writing it? I just kind of designed it in. Keynote.
I think you wrote all the parts for it, just and put it together yet.
Well, I don't see it in my copy there.
Tree collection core.
Oh, the tree collection thing? That's what we called it? I thought I called it the vault. Oh, I was the name of the variable.
Yeah.
The variable is called the vault. There it is. All right, so we have this this instance of tree collection called the vault, and then we have the current code. So we need to have a unique code associated with each of our screens in the app. So kind of the idea here is that let's assume you couldn't figure out how to pass serialized data through the extras in your app. What you could do is you could give yourself a global you can give yourselves a global tree vault, tree collection thing, and then query that guy for the individual subtree that this particular screen was in charge of. That way, all you needed to do was pass the secret code between screens, and we already know how to pass integers, right? So you can pass an integer through the extras, and then use that integer to look up the tree that's supposed to be displayed as part of that subtree. Makes some sense? So inside of tree collection here, we created a linked list of tree values, and so this is just an empty linked list at first. Then we have this add tree thing that takes in a secret code as well as a binary tree when we add a tree to the tree collection. And we have this thing called a tree value. And here's tree value. Tree value holds a secret code as well as a binary tree too. So this is operating off that idea of a binary tree 2 being a collection of binary tree 2s, right? So we're going to have the actual binary tree 2 structure, but then within that we're going to have the kind of the subtrees. We could have probably also pulled this off by just adding to our binary tree 2 a fourth variable for secret code or something like that. We could have done something similar. So that we had some sort of unique way of identifying the individual portions of a tree. There's actually something we do in 470 related to binary trees called lexical address, where it's effectively that. So take secret code and make it way more complex, and just say it's the lexical address gives you the depth where a tree is in the bigger tree, and then where it is. Is it the left child, the right child? Is it the left child, the left right child, the right left child, or the right child? So it gives you like two pieces of information. Depth and then position at that depth, in case that was interesting information to you. So remember that next semester in 470 when we talk about lexical address for kind of doing a markup, adding metadata to a binary tree. Okay, so let's go back here. So my tree collection, when I add a tree, I get two pieces of information, a secret code and a binary tree 2. I pack that together in this new kind of object I built called a tree value, and that gets thrown into my mappings. Then I have this ability to kind of search through my tree collection, where I just pass it a secret code, and it gives me the tree that is associated with that secret code. That makes sense? Okay. So that's what a tree collection is right now. So now when we first build our tree, let's go back to main activity here. I'm doing that up top. I just hard coded in there, right? Yeah. So here's where I'm building my tree. This is, let me minimize this. All right, so this is inside of onCreate, inside of main activity. I go ahead and ask for my an extra called my tree. We're probably going to update this to tree code instead of taking in, because we're saying, what if I didn't know how to serialize data and send it? Now what we're actually sending is the code for the tree that this guy's supposed to represent. So if I didn't actually have a tree codes, we'll go ahead and update that here. Call this my tree code. Make sense? Because in this version, the version where we're using the vault, we're not actually passing trees around. Our tree collection lives globally. What we're actually passing through extras is the secret code associated with each of our trees. All right, so I'll look for my tree code here. If I didn't find it, I'll go ahead and, here, we're going to be updating this here in a second. So if I have my tree code, I'm going to go ahead and say this dot my tree, and my tree is an instance of binary tree 2. We will ask this guy for, let's see, I need to think about how we're going to actually do this. Let's draw our picture. All right, so I have my binary tree here. Oh, I could just steal this binary tree. All right, so that's my binary tree. Now what I'm going to do is I'm going to encode this guy inside of a tree collection. So every one of my subtrees of this guy is going to be stored inside of my tree collection, right? All right, so what I need to be able to do is when I first go into the app, I build my tree. That's what this whole if else structure is doing. Okay, so in the event that I don't already have something being passed between my screens, forget about what that something is right now. If I don't have something being passed through my screens, I'm going to go ahead and initially build my tree. So now I have a tree. Now each screen in our application is going to show information about the current payload and the left and right child of that particular guy. Now we need to be able to retrieve that information from somewhere. All right, in the event that we were not able to directly ask extras for our tree, instead we were able to ask extras for our tree code, the secret code associated with the tree. We need to be able, we need to get that code and then be able to ask our, what I call a tree collection, for the tree associated with that code. All right, but now we want to think ahead one level. So let's say that I've gone ahead and I've gotten that top level tree that didn't have a code. So that's going to be, this guy right here. When I go ahead and get my initial tree code, I'm going to do some stuff here. It's not going to be a serializable extra. It's going to be an integer extra to get my code. And then I'll use my core.thevault to look that guy up. And ultimately, I'll get a binary tree too. Okay, and that binary tree 2 either has a left child or a right child. Make sense? If we go back to our tree collection up here, we have the ability to search for a tree given its secret code. But if I'm back out here like this and I click the left button, I'm going to be going to another version of MainActivity, right? Second instance of MainActivity that's going to show the left subtree of that guy. But what I need to do is I need to get the secret code associated with this left button. That make sense? I need that secret code because the only way I can get binary trees in this version of the implementation is by passing around the secret codes for those binary trees. Got it? All right, so if I'm on this first screen where I just created my binary tree. I know my top level thing is binary tree, is the binary tree I just created. That part's easy. And then I click left child, assuming that guy has a left child. When I click this, before I can go on to this next screen, I need to get the secret code associated with this screen so that I can pass it through extras. How do I do that? When do I add stuff to my tree collection? Okay, so when I first create the tree, do I also add it to the tree collection? Or do I add it to the tree collection as I'm traversing through the tree? I don't know if I can. We'll just go back to the base question of when do I put stuff? I mean, the question here is how do I use tree collection? I have this sad looking guy over here, tree collection, our vault. This is the vault. Okay, this guy's just sitting over here waiting to hold some information. Now, ultimately what the vault's going to hold is he's going to hold this 5 as a binary tree 2. He's going to hold this 3 as a binary tree 2. He's going to hold this 3 as a binary tree 2. He's going to hold this 8 as a binary tree 2, so on and so forth. He's going to hold a linked list of binary tree 2s. Now, those binary tree 2s are actually part of a binary tree 2 data structure. So we have multiple pointers going to the same place. We have these guys, they're all being held in this, this organized format, right? This is a binary tree, or we've called it binary tree 2 was our secondary implementation. Okay, so those guys already have links to each other. This guy has a left child of this dude. This guy's a right child of this dude. But now what we're going to start doing is we're going to start adding like a 5 here and a 3 here, so on and so forth. And we'll go ahead and just right next to it. I'll make these guys in red. Maybe this is secret code 0. Maybe this is secret code 1, something like that. All right, so my vault is holding a linked list of binary trees, completely disregarding the fact that this 5 is connected to this 3 and this 8 in our binary tree 2 structure. Okay, the vault doesn't have to worry about that. The vault's just going to say, here is the root node with the secret code you asked for. And it's going to have a bunch of crap potentially hanging off of it, but the vault didn't care about that. The vault was holding that top level, what did we call it? This guy was called a tree value, right? He was holding this top level tree value, which had a secret code and it had a binary tree 2, these 2 little pieces. So this guy right here is a tree value. This guy right here is a tree value. This is a linked list of tree values. Okay, so the first part of my question is when do I add my tree values to the vault? Is it fair to say that the vault is a secondary way of looking at my binary tree? What's the purpose of the secret code? Let's just think about the problem we're actually solving here. What's the purpose of the vault along with the secret code? What problem am I solving with the existence of the vault? If I was unable to pass an actual binary tree 2 from this screen to this screen, but this screen needs a binary tree 2, the job of the vault is I pass an int from this screen to this screen and then let this guy look up the binary tree 2 that he's supposed to show. Does that make sense? Look up the binary tree 2 that he's supposed to show given the secret code. we already know we can pass integers around, right? We can pass integers around our application. That's nothing new. We didn't have to deal with serializable stuff and things like that. So we can put extra secret code, or tree secret code, whatever I called it, and pass that along. So up on the very first screen, we first create our binary tree 2. Do I have the binary tree I want to show? Right off the bat, when I come in here, let's go to MainActivity. If I didn't find a tree code, I'm going to go ahead and build a binary tree 2. Do I then have the actual binary tree this particular copy of MainActivity should show? I have it, right? I didn't have to look that up in the vault. I built it right here. This is my original copy of my binary tree 2 is right here. Make sense? Okay. So I have that guy. But if I came in here and I said, oh, wait a minute, I have a tree code. That means that I need to look up in the vault the binary tree that I'm supposed to show. So let's get this in 2 pieces. So we're going to go ahead and say int my tree code is equal to this dot get intent dot get int extra, and this guy was called my tree code. All right, so that's the secret code that we're getting from that guy. We didn't pass it as, we passed it as integers, didn't we? Oh, I guess we haven't passed it at all yet. I should be able to get it int extra. Oh, it's a default value. So we'll pass it that, and then in the event it couldn't find it, we'll just give it a -1. That's fine. If you did it with a string extra where you passed around string versions of your secret code, that's fine. It's not a problem. Then you would have had to actually you wouldn't even have had to convert it to an int. So if you did it the other way, if you would have said string my tree code 2 is equal to this dot get intent get string extra, and then call this guy my tree code, something like that, then you'll get the string representation of that number, assuming you set it as a string. So when you set the code, let's say it's secret code 4, you would set it as the string 4 instead of the int 4. Pick your poison, same thing. What did we do inside of our tree collection or tree collection? Oh, I wrote it such that it takes in a string. So we'll have it take in a string. All right, so doesn't matter just how we're representing the code. Is it an int or is it the string version of an int? All right, so I'll say this guy right here. My tree code, we'll get the intent, we'll ask for the string extra called my tree code. That's only if he has an extra called my tree code. All right, so we'll go ahead and extract that tree code. Then we ask the vault for the tree associated with that code. core.thevault.get tree with super secret code, my tree code. Make sense? So if this particular instance of MainActivity had a tree code, we're going to use that tree code, we'll retrieve it, and then we'll use it to look up the binary tree that we are supposed to show on this version of MainActivity. If we didn't have a tree code, it must be that we're the very first time through here. And what are we going to do? We're going to just build our tree the very first time. We didn't need to look it up in the vault the very first time, right? We have the tree. Nothing to look up. We have our tree called my tree. So any way you cut it after this if-else structure here, this dot my tree is equal to a binary tree 2. It's either equal to the one we looked up from our vault, or it's the one we just built fresh the first time. Make sense? Now, all the rest of the code we already wrote here should already work for showing a local version of this.mytree on the screen with the correct buttons turned on and things like that. So we need one more change. That is when we hit a button. So this is us hiding buttons and stuff like that. But these two functions down here, if we hit the left button, we hit the right button, we no longer are putting my tree as an extra. We pretended like we could not serialize binary trees. We didn't know that we were allowed to do that. So instead, what we need to do is we need to add the binary tree that's the left child, or add the binary tree that's the right child to the vault, along with the next secret code. Then we need to add that secret code to the extras. So the name of our extra here was called myTreeCode. So we're going to put an extra here called myTreeCode. And myTreeCode is going to be core.currentCode. So we'll go ahead and get the current code is going to be the next code that we should store. So that's where we're putting in the extras. Then once we add it to the extras, so that's us passing to the next version of MainActivity. That's us passing it the secret code. Like, here's your ticket. You can look up your binary tree when you arrive at the station. Make sense? So we're handing him his ticket right here. Then we're going to go ahead and say core.thevault.addTree. Okay. Now the tree we're adding, let me just real quick make sure that core is a string. No, we store that as an int. So we're actually adding the extra here. Empty string concatenated with current code. So we're passing those guys around as a string, I guess. Passing around as an int probably would have made more sense, but it doesn't matter. Strings are easy to work with. So now we're going to add to the tree. Now adding to the tree takes in a string version of the secret code along with the tree that we're storing. So the string version of our secret code is this guy right here. So that's the empty string concatenated with core.currentCode. And then the tree that we're representing for the left subtree is this dot mytree.left. And the one thing we need to make sure we don't forget to do is core.currentCode++. That way the next time somebody goes to get a secret code, it's a unique secret code. It's the next secret code in the sequence. Make sense? So that's what we do when we traverse from screen 1 to screen 2. Instead of passing the tree directly through the extras, we get a secret code, we set that tree up in the vault with that secret code, then we pass the secret code. And then when we get to this guy, we look up the tree associated with that secret code. That's what we did right here. If I have a secret code, grab the secret code, then look up that secret code in the vault. Give me the tree associated with him. So as we walk through our tree, hitting our buttons, our left and our right button, we grab the tree that we're supposed to go to. We say, well, how do I get this to the next screen? And because we don't know about serializable, we have no way of getting it there. So instead we say, look, you get it now? We have no way of getting it there. So instead of trying to somehow shove it into the trunk of the car, okay, you know, this is kind of like when you buy a washer or dryer and you won't fit in the trunk of your sedan. Mm-hmm. You know, they give you a little receipt that you go to your house and then they come with a delivery truck and give it to you. The delivery truck is the vault. You're sitting there with a nice little receipt that fit in the trunk of your car. It'd be weird if you put the receipt in the trunk of the car, but you can do it. Mm-hmm. Right? So we grab the secret code from the intent and then we say, vault, here's my code. I'm ready. Drop it in. And we get it right here inside of this .mytree. Make sense? So we're just passing around secret codes and then looking it up. For our left button click I'm going to just steal almost all the same material. Except we're passing the right subtree. So here's the intent, putting an extra into the intent. My tree code is going to be a string extra because that's what how we're passing it, whatever. So we have our string extra. Then go ahead and actually add the tree to the vault before we jump. So we're passing some sort of useless code that never actually got added to the vault. We'll be in trouble, right? We'll go to look it up and we'll get stuff. Then make sure we increment our code so the next time around we get a fresh code. I mean, it's possible, depending on how many times you go through, go from screen to screen and back and go back through, that you might actually add the same binary tree too, the same pointer to the vault 15, 20, 30 times. But each one will have a unique code. I mean, who cares if it was the original left subtree that has, 19 secret codes that point to the same place? Doesn't matter as long as you're getting the right tree. Okay? And we'll start the activity. All right, so the only thing we had to do here is instead of retrieve the tree, we retrieved the code and looked up the tree. Down here, the only thing that we did is instead of putting the tree as the extra, we put the code as the extra and stored the tree. So I think at the end of class last time I told you it was something like 4 lines of code, 5 lines of code, something like that. All right, so we'll go ahead and run this guy real quick. It's really funny you say that. I don't know. I don't even know where it came from. Last night when I was walking around the house, we were watching TV, and I kept asking my wife. I said, "Do you think Mr. Gonzalez is juicy?" For no good reason, just just kind of a weird question, right? But then when you just asked that, it's kind of funny. I probably said it 10 times last night until she started getting annoyed. That's when I took the picture of him with his butane torch.
Is that the front?
Yeah. Is it dying? Oh, I just have to click it. All right, so I go to left child. It creates the new code by just adding 1 to my integer, stores it in the vault. This guy has a left child. There's my left child. He has no way of getting back. Now, when I hit the back button, I'm not removing this guy from the vault. I'm basically just saying he's already used that code. I'm just going to keep that pointer up there for no good reason other than laziness. So I go back. I'm at this level. I'm going to go back at this level. So I have a couple of things still sitting in my vault with secret codes that I no longer have access to. Because that secret code lived and died with the intent for those 2 main activities that I just killed off. Yeah, I mean, those intents are no longer around, and I've already incremented core.current code. I can't get back to current code 1.
So then does that the thing that you store in the vault still there in the vault?
Mm-hmm.
Okay.
There's no big deal. Oh, man, bacon. There's my right child, my left child, whatever. I think this looked like the tree. All right, so that makes sense? How we accomplish that? Anybody do it in a really bad, weird way?
I think mine might have been. Well, I didn't use extras
Okay.
because I thought
You had an aversion to extras, it seems like. You didn't want to use extras last class, and you used a stack.
The first time I didn't know about them. The second time I got confused and thought we were.
No, you didn't. You knew about them, you just didn't remember them.
Sure, I didn't remember what they were called.
Because we definitely did extras. We've definitely done extras, okay? So you're still using your stack up in...
No, I used your way this time. Because so what's the point in this case for using an extra if we have everything stored up in core already?
Well, you
You
still
can
need...
just access it there.
Okay, so what you did is rather than passing, in this particular case, in this particular implementation, you can pull that off because you only need to know about one secret code at a time. So you just had a single secret code you stored up in core rather than passing it through here because we weren't worrying about cleaning up our mess. We didn't have to worry about keeping track of the 11 different, if we really wanted to be unique about it, we could have asked the question of, is my particular instance of main activity, do I already have a code? If I already could, because in that case, we might not want to have, we might want to have multiple instances of codes, right? So, but in any case, this was a workaround in the event that you, and it wasn't a difficult workaround. We just said, look, I don't know how to store binary tree twos in extras. Or in Blaine's case, I didn't know that there were extras. It's like buying a car and never using the trunk. It's like,
what's that for?
What is this thing? Okay, so, but the point is that one way or another, you need to be able to get instances of binary tree 2 over to the next screen. One way or another. So, we're computer scientists. We, solve problems using the tools we have available to us. He lost the key to the trunk. Didn't even get to the point of looking what would fit in the trunk. I'm not even opening that thing. It could be a body in there or something, right? And just said, I'm going to just implement it up in a singleton. It's fine. Yeah, it's no problem. Really, if you're going to do that, though, you didn't even need a secret code or a vault. You could have just put whatever the next tree was.
Yeah.
We didn't need to do any lookup crap, right? You're storing one piece of information and looking up one piece of information. You might as well just store the piece of information you were going to look up. So what I'm getting at with that is he could have just put up here public binary tree 2, call this guy cur tree, something like that. Start that off as null. And then inside of main activity, we would have just asked the question, instead of this guy right here, we would have asked the question, if core.curtree, is that what I called it? Core, where's core? Yeah, I called it curtree. Oh, thank you. If core.curtree is not equal to null, then we'll just say this dot my tree is equal to core dot curtree. Else do all this crap, build my tree. And then down here, when we click on a left or a right button, instead of this stuff, we'll just say core.curtree is equal to, this wouldn't work as well because you would have to do it as a stack. Because when we come back to the screen, we've lost access to, so if I say this is this dot my tree dot left, and same thing down here is core dot curtree is equal to this dot my tree dot right. Actually, we'll be okay. Yeah, this works because we've already gotten our local variable. We still need our intent here, though. All right, so still need our intent. We're not doing anything with extras because Blaine didn't know there was a trunk. And instead of storing any sort of secret code or using the vault, we'll just store what the cur tree is up there in the in core. There's our 5. There's our 3. There's our 3. Now when we hit back, yeah, you can, because when you hit back, you're thinking, oh, well, core dot cur tree, whatever, is the wrong cur tree. But this dot my tree is still accurate. So when I go back here, this guy has the correct this dot my tree. So we only use core dot cur tree inside of onCreate, which happens one time, not every time it shows up. So I can still walk back up to the top here. That makes sense? That actually probably would have been the easiest version of the original assignment. Less not cool, because you didn't get to use serializable, you didn't get to use the vault. But you really only needed one. I mean, we're not even using, you go up to core, we're not using either of these. We're just keeping track of what the current tree we're showing is. Make sense? So there's some ways you can do this crap. All right, questions about that? Now, what do you think? Tell me what you think we learned in this exercise. What's the hard part about wrapping our mind around it? It's related to what we just talked about, like, oh, didn't we lose track of which tree we're currently working with? What have we taken away from this assignment? If I asked you to write like a couple of paragraphs of what did you learn from this assignment? Or maybe what were you supposed to learn in this assignment? Let's go that route. Okay, so that's pass by value versus pass by reference. Kind of already knew that, but reinforce that. It's fair. What else? There's kind of one concept that we hadn't previously explored. What is this guy an instance of right here?
MainActivity.
What is this guy an instance of right here?
MainActivity.
What is this guy an instance of right here? Well, those are 3 separate instances of MainActivity, right? That each have their own state. That each have their own version of this dot my tree. Does that make sense? So that's one thing we learned. And then we also learned how these things are organized. When I walk through my tree here, right now I have exactly one instance of MainActivity that exists. Okay? When I hit left child here, what happens is I create a brand new instance of MainActivity. The old one's still alive and kicking. Okay, but I create a brand new instance and I push it onto the top of the previous MainActivity. What kind of data structure do I push things onto? Stack. Okay, so the activities are represented as an activity stack in Android. So when I hit left child, I create a new instance of MainActivity, not touching the current instance. Current instance is perfectly safe. He has his own copy of this .my tree. When I hit left child, I go here. So now what's happened is an Android app always shows the activity that's at the top of the stack. Make sense? So that other one's still there. It's laying underneath it. My first screen that had the, what was it, a 5? That had the 5 on it. It's still there. It's still even showing the 5. I just don't see it because I'm only actually rendering the activity that's at the top of that stack. Now, if I hit back, back is the default action of back is to what? Pop the top of the stack. So I hit back here, it pops the top. Oh, that was like a Beyonce thing, right? That's a Beyonce thing, isn't it? Beyonce? Is that just high school girl thing? It's like the sassy. I feel like I'm pulling it off. am I not pulling it off? So when I hit back here, I pop off the top of the stack, the current thing that's being shown, and destroy it. It's going away. Automatic garbage collection is doing it for me. It's doing the cleanup, so there's probably some sort of small period of time where that guy's still floating around, something like that. But from my perspective, from the programmer's perspective, it's dead. So when I hit the back button here, I pop the top of the stack. That guy goes away, and now Android always shows the current top of the stack, which was the guy that was laying underneath it. When I hit this button, I create a new instance of MainActivity. I push it onto the stack. When I hit this button, I create a new instance of MainActivity. I push it onto the top of the stack. When I hit the back button, it pops from the top of the stack, destroying that copy of MainActivity, showing me the current top of the stack, which was the previous screen. When I hit back, this pops the top of the current activity stack, destroying it, showing me the new top of the stack. If I hit the back arrow again, what will happen? Why?
Because you were outside of the app before you entered it.
If I have a stack with one element in it and I pop that one element, what am I left with? I'm left with the empty stack. And if Android applications show whatever's at the top of the stack, this closes the application. Make sense? Now, have you ever been in one of those apps, whether it's iOS or Android, when you hit, actually Android is where you see this the most, where you hit the back button and it actually brings up a warning saying hit the back button again to actually quit the app? What they're doing is they're overriding that on back pressed function that we've done it in here, saying, whoa, 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 you are about to pop the top level of the app off the stack. Are you sure this is what you want to do? So they're interjecting. They're not just letting the default behavior of the back button take over. They're saying hit the back button, like, oh, wait a minute. That's what you want. Hit it again if it's what you want. They're probably setting some flag that said checked with them. And then the next time they hit it, they say, well, if haven't checked with them, check with them. Else, if I did check with them, then call super.onBackPressed. And it'll just do the default behavior and make the app end. Make sense? That's the organization of an Android application. Okay, questions about any of that stuff? All right, so let's create a new project. In 250, did we ever do a project called Cave Crawler? Okay. Sometimes I introduce it as a text version in 250, not dealing with JSON, but we'll. I'm going to create a new project. It's going to be an empty activity. We're going to call this guy Cave Crawler. Okay. One other thing to ask. Did we do file I/O in here? Are you sure? Kind of remember reading in Bible books.
Oh, you mean the...
Reading stuff in from a file.
Probably did that one.
Didn't we store all Bible books inside of a file? And are you relying?
I don't think so.
I
I think you mentioned it. We haven't done it.
You might have mentioned the option, but we never actually looked at it.
Like you used it.
I have a really good memory. Hold on, let's.
I know we talked about it, but I don't know if we actually.
We never did. We used it in class, but we didn't do anything with it.
It was right before Easter break.
Maybe it's like homework over Easter.
I didn't give you homework. We did it in class.
Yeah.
But we wrote it and it worked. Yeah, look at that. File input stream. BibleBooks.text acts as you should ask and you shall receive. All right, so we put inside of downloads BibleBooks.text. So we created a text file and put a bunch of Bible books in there, right? that I copied from the web. I said, let's say you had a whole bunch of data that you wanted to get into your application. All right. And that data lived someplace else, lived on the web, lived wherever. So we found a list of all the Bible books, and we could have pasted it into our app and put it as a string and all this stuff like that. But instead, we decided to write it this way. All right. So we put it into a text file and then just read it into our app, and that allowed us to get it into string format. All right. So we're going to kind of look at two things here leading up to our cave crawler. One of the things is we want to be able to read in JSON from a file. All right. Now, just because we're reading in a JSON string, remind me, what's a JSON string?
A bunch of data stored in
Okay. How's the data stored? There's a structure to JSON. What's that structure look like? I'll give you a picture of it, and then you can try to describe it to me.
Oh,
Okay. So this is kind of like a Python dictionary, right? All right, so JSON stands for JavaScript Object Notation. So this is how the JavaScript programming language represents its objects. This is also how, when we store things in Firebase, or we pass things through extras as serializable objects, this is when we serialize an object, this is what happens. We turn that object into JSON. We turn it into name value pairs of its public fields. Make sense? Now, JSON here supports, so if we kind of look at this and try to understand how we read it, it's a curly brace based format that kind of screams. This probably came from programmers. Who's the old school competitor to JSON? XML. Yep, old school competitor to JSON is XML, which is a tag-based language, right? And when we looked at XML last semester, we kind of saw that it's got a lot of fluff. To store relatively small amounts of data, you have a whole lot of tags on either side of that data, which is fine. I mean, text isn't that big. We don't care with data storage and how fast our internet connections are and stuff like that now. It's not that big of a deal. But we can certainly, as a human being, look at it. It's kind of like getting a giant piece of Tupperware to store like a spoon. Just one spoon. Just toss it in there and slide it under the bed and just says spoon. Put a piece of tape on it. Not spoons, just spoon. And you get one of the giant ones that was like on sale at Home Depot that they couldn't sell. You know what I'm talking about. All right, so XML we're going to say is kind of inefficient in that it's got a lot of structure to store a relatively small amount of data, where we can look at JSON and say this is more streamlined. My structural pieces here are really just curly brace stuff. We also have these square brackets. I'll talk about that here in a second. But for the most part, it's curly brace stuff. And we store name value pairs. So most of my structure is this curly brace stuff. And then I have, here's the name of a field. All right, so if we think about this, if we try to kind of map this back to an object, that we wrote. Let's say we wrote a Java object that had some public fields. This particular object has, its name is page info, and it is of object type. What kind of value is that, what I have highlighted right there? Look at the structure. It's a dictionary. It's JSON. It's JSON. As opposed to, here's a name, here's a value. So the value type of this name is a string. So post ID is a string. Actor ID is a string. So these guys are all name value pairs, as Luke pointed out, right? Name value pair, name value pair, name value pair. Name value pair. The value associated with page info is an object type value. How do we know? Because its type is JSON. So the object associated with this is an object that has a page name, that's a string, and a logo, that's a string. So it gives you the URL to where that logo lives. All right. So if we were to write this, if we were to like internally deserialize this, or what's the computer science term for deserialization? Marshalling. If we were to marshal this ourselves, we would what are we trying to do here? What's the name of this thing? This is page info posts. Okay, so we're gonna call this a screen object. So I'm gonna go back. Go ahead. Nope.
There's a-
You're talking about the square brackets. That's for arrays.
oh, for-
Yeah, so JSON, this is where JSON differentiates itself from XML, is JSON supports arrays. So posts here is a collection of. So this is an open square bracket, closed square bracket. In a C-style language, square brackets scream arrays to us, right? So this is a collection of post objects, in this case, and there's only one of them in there right now.
you were saying there's like something similar to that and can be like 2 or 3.
Well, yeah, so I'm going to turn this back into a rough version of this in Java, just to kind of see what this looks like. All right, so we're going to call this guy called screen.java. I'm just making up what this JSON is representing. It's a screen in an app or something like that. All right, so I'll left justify this guy. So this will be public class screen all right, and then we have a variable called page info whose type is maybe a page object. So we're going to have a page info. And then we have a variable called posts, whose value is going to be an array of post objects. So we have a post array called posts. And that guy holds a collection of, we would call this a post class. So our post class, I'll just go ahead and write this below here. Public class post. A post has a post ID, which is a string. It has an actor ID, which is also a string. It has an author name and a post title. It has comments, which is going to be, I'm guessing that's going to be an array of strings. They don't show us any comments in there, but kind of makes sense. A comment might be an array of strings. So we'll have a string array called comments. And then a time of post, also a string. So this JSON, when marshaled back into actual objects, I haven't given them their values here, gives us a object structure that looks like this, where we have a class called screen, for example, that holds 2 fields, a page info, that's a page object, whatever a page is. Actually, we can go ahead and write page here. Public class page. And a page holds a page name and a logo. So that's what a page is. So we have a screen that holds a variable called page info of type page, where a page is an object that holds a string page name and a string logo. And then it has an array of post objects called posts, where a post object holds all this information about an individual post. Does that make sense? So do you see how JSON represents an object notation from a programmer's perspective? JSON stands for JavaScript Object Notation. So the JavaScript language decided, hey, this is a pretty reasonable format for storing the structure of our objects as strings. Make sense? Okay. So what we want to be able to do here, I'm going to copy this code here just for our sample. We created a new class here called Cave Crawler. Now, when we did file I/O before, we did it inside of Eclipse. And remember how we kind of had to be weird and give it the full path to where the file is? Now we want to see how do we do that with Android in terms of resource IDs. So I'm going to go under resources here. Did I just do it in resources? Right click on resource. I'm going to create a new file. All right, and we're going to call this guy input.json. Okay, and where did it put that guy? He put it somewhere. Okay, put it inside of my resources folder, but it doesn't show up under resources here. So I wonder if it needs to be in a different place to show up. I'm going to close it here. I'm going to cut it. And then I'm going to go up a couple levels. Let's go to main. I don't know if I want to put it right in my here. Out of curiosity here, I want to try something. I put it in resources. Let's see if it auto mapped it. R dot ID dot, what did I call it? Input. Let's see where Android wants us to put text files. Because what we want to do is we want to read in our JSON from a text file. All right, so I want to put it into, this is getting it from like an SD card. Okay, it looks like it wants, we have something called raw. Add resource directory. Raw. All right, so under resources, I'm adding a resource directory called raw. And then I'm going to right click on raw, just create the file again. I'm going to create a new file. I'm going to call this guy input.json. Okay, there it is. Just real quickly, I'm going to go delete the old one. So this is the old one that we put in there. Now we have a new folder called raw, and it wanted us to put that in input.json. Okay, so ultimately, I'm going to go here to my JSON code. I copied it already. And I'm just going to throw that stuff into my input.json file. Because if I were to read this all in and wanted to put it inside of a string, I actually think Android Studio does a pretty good job of this, where if I said, no, I already have it highlighted. If I came in here and I said string s is equal to that, and I put that in there, it will go ahead and escape character everything for me. Okay. This is a great service Android Studio is doing for us by doing escape characters and all the double quotes and things like that. We would have normally pasted that in. It would have just been this jumbled wad of text. And then we would have had to go through it every single place where we had, a double quote, where we actually want the double quote to be part of the JSON, not the beginning or the end of a string. We would have had to put a little backslash before that, and a backslash before this, so on and so forth. We would have had to put all that in there. All right, so Android Studio is doing quite a bit of the extra tedious stuff for us, but it doesn't matter for us because we want to be able to read this in from file.io. Okay, so what we're going to do next time is we're going to have our input.json here. We're going to read from this file into our code. So bring it in as a string, and then we're going to use the JSON parser to parse that. That will prove that we have the ability to, what we're going to do is we're going to represent a graph. We're going to represent a dungeon, a cave crawler in JSON that's going to have, there's a room to the north, there's a room to the east, there's a room to the west, there's a room up. We're going to be able to design the structure of our cave, read through it in JSON, parse it, and then ultimately, build a structure for it, build an interface for it where we can walk through our cave using an Android app. All right. Remember, was it Thursday is the hackathon? Mm-hmm. So Thursday there is a hackathon. Go online. It's 3 hours. It's here on campus in the Albrecht Lounge, hosted by the Commons from downtown. There should be good networking opportunities there for possible internships, stuff like that. We already have a bunch of people signed up, but if you haven't signed up yet and you're able to go to it from 3 to 6, go onto Slack and follow the sign-up link. I'll be giving you a homework assignment on Thursday, due on Tuesday, and there will be a portion of that homework assignment that you will be able to omit if you upload a picture of you at the hackathon. Okay? It's not a penalty portion. I'm not going to make it some impossible part, but there'll be a feature of the assignment that you could choose not to do. I'd still encourage you to do it, but you could choose not to do in exchange for the 3 hours you spent at the hackathon. All right, but get signed up for that as soon as possible. Also remember, today's student, faculty, staff, Bible study, God, and grub. Go to the cafeteria, sign in. Take your tray down to the terrace room from noon to 1. I will see everybody on Thursday.